It is important to understand the difference between heat and temperature. Temperature is a way of describing how hot or cold an object is and is measured in degrees Celsius, whereas heat is a form of energy and is measured in joules. If more heat is provided to an object, the temperature of an object will rise. So heat and temperature are related, but they are not the same. Have you ever thought how much energy a kettle uses to boil an amount of water? The amount of energy transferred depends on three things: the amount of water, rise in temperature, and a term known as specific heat capacity or heat capacity of water. These factors are the reasons why it takes longer to boil a lot of water than if you boil a small amount of water. Apart from other factors, the key factor is heat capacity. Heat capacity is defined as the amount of energy required to raise temperature of an object by 1 degree Celsius. However, more useful is to think about specific heat capacity of a substance. This is, as it says in the name, a little more specific. It is the amount of heat required to raise temperature of 1 kilogram by 1 degree Celsius. Water has a specific heat capacity of 4.18 kilojoules per kilogram per degree Celsius. This means it needs 4.18 kilojoules to heat 1 kilogram up by 1 degree Celsius. Different materials have different known specific heat capacities, but we're not always given table like this. So we need to be able to calculate the value of specific heat capacity ourselves. For this, we have this equation: energy equals mass multiplied by specific heat capacity multiplied by temperature change. In essence, the equation states that energy transferred is dependent on the mass, specific heat capacity, and temperature change of an object. The equation can be rewritten as symbols like this. Energy transferred E is the heat energy absorbed or released. This equation can also be rearranged. To work out the temperature change, simply subtract the old temperature from the new temperature. Let's have a look at an example. We have to compute the specific heat capacity of lead with the data in the example. Have a look at the equation and the question. The energy transferred is 3840 joules. Mass is 3 kilograms. And the temperature change is 10 degrees Celsius, which is 50 minus 40 degrees. Using the rearranged equation, substitute the value, and we get 128 joules per kilogram per degree Celsius. Here is another practice problem. In this, we have to calculate the energy transferred to the lead. Energy transferred is equal to specific heat capacity 500 multiplied by mass 5 kilograms multiplied by temperature change, which is 15. 5 minus 20 degrees. We could divide by 1000 to convert the answer into kilojoules, represented by K and G. Note, the answer is negative this time instead of positive. This is because we cooled the lead. The temperature change will always be negative when cooled and positive when heated. Different materials have their own specific heat capacity, and this has consequences in our everyday life, which we might not be aware of. Most of us probably cook with water more often than we do with oil. Imagine we are heating both water and oil over identical heat sources. Specific heat capacity of water is 4.18 kilojoules per kilogram per degree Celsius, and specific heat capacity of olive oil is 1.97 kilojoules per kilogram per degree Celsius. What temperature rise would you get for each if 1 kilogram had 40 kilojoules of energy transferred? If we rearrange the equation, delta theta is the temperature rise. For water, we get 9.5 degrees Celsius, and for olive oil, we get 20.3 degrees Celsius. Olive oil has much lower specific heat capacity than water, so it heats up much quicker when exposed to identical heat source. In fact, when exposed to the same heat source, identical mass of oil heats up almost twice as fast as water, reaching 200 degrees Celsius, while water is still boiling. The table below shows the specific heat capacities of a range of substances. Notice how the value for metal gets lower as atomic mass increases, and the materials made up of lighter elements have a much higher specific heat capacity. To calculate energy transferred, we use the equation delta E equals mass multiplied by specific heat capacity multiplied by delta theta. This will give us the energy needed to boil a kettle of water. If we take zero point 0.5 kilograms of water at 18 degrees Celsius and heat it to boiling point or 100 degrees Celsius, then energy used equals 0.5 times 4.18 times 82, which equals 171.380 kilojoules. Notice this assumes that there is no loss of energy during heating, which of course is not accurate. Heat and sound will be lost to surroundings. If this kettle took 80 seconds, we can begin to estimate the power of the kettle. Power is the rate at which energy is transferred. Power equals energy divided by time. So we get 171.380 divided by 80 equals 2.14 kilojoules per second or 2.14 kilowatts. In most examination questions, you will be given energy and might be required to compute the power using the above steps. However, the steps can flip as well, meaning the question might state both power and time. You might be expected to compute the energy using the equation power equals energy divided by time. In other words, energy equals power multiplied by time. We will now briefly discuss the heat capacity of an object. It is defined as the amount of energy needed to raise temperature of an object by 1 degree Celsius. Note the absence of the word specific from the definition. This means that heat capacity is not concerned with raising the temperature of unit mass by 1 degree Celsius, but in raising the temperature of the object as a whole. The concept is useful in determining the amount of energy transferred in both heating a substance to a specific temperature or cooling a substance to a lower temperature. The energy transferred is computed as energy transferred equals heat capacity of an object times the change in temperature. The equation is almost identical to the one for specific heat capacity, with the exception of mass, which is excluded from the computation.